In a quiet room in Veldhoven, in the south of the Netherlands, a machine the size of a city bus is being assembled by hand. It contains more than 100,000 individual parts. It costs upwards of $350 million, and there is exactly one company on Earth that knows how to build it. That company is ASML. Inside the machine, droplets of molten tin fall through a vacuum roughly 50,000 times every second. A laser strikes each droplet twice, once to flatten it, once to vaporize it. The tin explodes into a plasma hotter than the surface of the sun, and in that instant it releases a very particular kind of light. Extreme ultraviolet, with a wavelength of just 13.5 nanometers. That light is so short, so fragile that ordinary glass lenses would simply swallow it. So the light is guided instead by mirrors polished so precisely that if one were scaled to the size of Germany, its largest bump would be less than a millimeter tall. The mirrors are made by Zeiss in Oberkochen. They are, by many measures, the flattest objects human beings have ever manufactured. The light bounces through this hall of mirrors, strikes a patterned mask, and finally lands on a polished disc of silicon, and it draws. This is lithography, printing with light. It is the beginning of everything that follows. The silicon wafer travels to Taiwan. On the western coast of the island, in Hsinchu and Tainan, sit the fabrication plants of TSMC, the Taiwan Semiconductor Manufacturing Company. Inside, the air is filtered until it is thousands of times cleaner than a hospital operating theatre. A single speck of dust landing in the wrong place destroys a chip worth tens of thousands of dollars. TSMC does not design chips. That is the crucial point. It manufactures them for others, a foundry, a contract builder in silicon. And it has become, quietly, one of the most important companies in the history of industry, because it is the only firm producing the most advanced logic chips at meaningful volume. A wafer entering a TSMC fab will pass through the machines hundreds of times over roughly 3 months. Layer upon layer, deposited, etched, patterned, polished. Transistors are laid down by the tens of billions on a piece of silicon smaller than a playing card. The features are now measured in single-digit nanometers, a scale where a wire is only a few dozen atoms wide, and where the ordinary rules of electricity begin to fray. But what shape do those transistors take? What are they meant to compute? That question is answered somewhere else entirely. In Santa Clara, California, sits NVIDIA. It owns no factories of consequence. It builds nothing with its own hands. What it produces is design, the intricate blueprint of a graphics processing unit, a GPU. The insight that made NVIDIA the most valuable company on Earth was deceptively simple. A traditional processor is built to do one difficult thing at a time, very quickly. A GPU is built to do thousands of simple things at once, in parallel. For decades, that was useful mainly for rendering video game worlds. Then researchers realized that training a neural network is, at its heart, the same operation. Enormous grids of numbers multiplied together, over and over billions of times. But hardware alone was never the moat. In 2006, NVIDIA released CUDA, a software layer that let ordinary programmers write code for these parallel processors without understanding graphics at all. For nearly 2 decades, universities, laboratories, and startups built their tools on top of it. Today, the overwhelming majority of AI research runs through CUDA. Competitors can match the silicon. Matching 18 years of accumulated software is a different problem entirely, which brings us to the challenger. AMD, also headquartered in Santa Clara, a few minutes' drive away, designs both CPUs and rival GPUs, the Instinct line, built for exactly this market. Its hardware is credible. Its memory capacity in some generations exceeds NVIDIA's. What it has fought to build is the software ecosystem around it, an open alternative called ROCm. The contest is not really about transistors. It is about which platform the world's engineers choose to trust. And beneath both of them, invisible, sits a British company that designs almost nothing you can hold. ARM, based in Cambridge, England, does not manufacture chips. It does not, in the main, sell chips. It sells instruction sets and architectural designs, the fundamental grammar by which a processor understands a command. Apple licenses it. Qualcomm licenses it. NVIDIA's own data center CPUs are built on it. ARM-based designs ship in the tens of billions of units each year. It is the quiet grammar underneath the modern computing world. Now return to the GPU itself and look closely at what surrounds it. A processor is only as fast as the data you can feed it. And a large AI model contains hundreds of billions of parameters, each of which must be fetched, multiplied, and returned constantly. Ordinary memory cannot keep pace. The chip would starve. The solution is high bandwidth memory, HBM. Instead of laying memory chips flat beside the processor, they are stacked vertically, 8 or 12 layers high, drilled through with thousands of microscopic vertical connections, and placed directly alongside the GPU on a shared silicon base. 3 companies in the world make it at scale. SK Hynix in South Korea, which pioneered the technology and dominates its supply. Samsung, its enormous domestic rival, and Micron in Boise, Idaho, the last major American memory manufacturer. For a period, HBM was the true bottleneck, not the lithography, not the logic, the memory. The finished assembly, logic, memory, packaging, leaves Taiwan and travels to warehouses that no longer look like warehouses. Microsoft, Google, and Amazon buy this hardware by the hundreds of thousands of units. They install it in data centers in Virginia, in Ireland, in Oregon, in Singapore. They wire it into racks, connect the racks with high-speed networking, and cool it with rivers of water and walls of moving air. A single large facility can consume as much electricity as a small city. And then, at last, the process reverses. Text scraped from the internet is fed through those chips. Weights are adjusted, gradually across weeks of continuous computation. And a model emerges, one that can write, translate, reason, and answer. Consider the chain in full. A Dutch machine, using German mirrors, prints an American design onto Taiwanese silicon, wrapped in Korean memory, licensed on British architecture, and installed in an American data center. Remove any single link, and the chain does not slow. It stops. There is no second ASML. There is, at the leading edge, no real second TSMC. This is not a supply chain in the ordinary sense. It is a sequence of monopolies and near-monopolies, each dependent on the one before it, stretched across oceans and political fault lines. We speak of artificial intelligence as though it were software, weightless, placeless, conjured from mathematics. It is not. It is tin and light and silicon and water and power. It is a physical object, built by perhaps a dozen companies who must all keep functioning at once in a world that offers no such guarantee.